Okay. About yesterday's lesson, it's not converting for some reason, like the unconverted, like room file there, but it's not converting to an MP4 for some reason, I don't know why. So I'll keep trying. I don't know if maybe there was a Wi-Fi issue or something. I'll keep trying to convert that. And I'll post it if I manage to get it. Okay, so the first one they ask you to prove that x equals, that x plus 3 is a factor. So remember, if they ask you that, then x plus 3, the bracket will give you x equals negative 3 as a value. So you have to sub in negative 3. All right, and the way of proving is that bit that I highlighted in yellow. If they ask you to prove that it's a factor, you do that. You sub in the value, you show that it's equal to 0, and therefore it's a factor. Okay, that's all you actually have to do for the proof part. Yes. And then so we are not. So what we're calculating is the remainder, even though they didn't make the thing equal to 0. Okay, so then they said also prove that it's a factor and then factorize fully. So guys, if you know that x plus 3 is a factor, that's going to be your first bracket. You don't have to again check and find something that makes it 0. All right, so x plus 3 is your first bracket. From there, you ask yourself, what must I multiply by x to get x cubed? That's x squared, right? For your middle term, you currently have 3x squared. You need 2x squared, so you need a minus x squared. So that's why that's negative x. And then what must you multiply 3 by to get negative 6 is negative 2. And then from that, you just need to, or from there, you need to factorize that trinomial. So this one wasn't difficult to factorize really. It was factors of 2, and then the difference between those factors must be negative 1. So if you have one positive and one negative, right? That's what that means. So negative 2 plus 1, that will give you negative 1. Guys, please, if you say therefore x equals negative 3 or 2 or negative 1, draw lines through that line. They didn't ask you to solve for x, they just asked you to factorize. Okay, so if you now decide, okay, I'm going to make this equal to 0 and solve for x, that's something that wasn't given. Okay, so it's very important. If they're asking you just to factorize, then this is where you stop, where you have your 3 brackets. Yeah. Okay. Yeah. Okay, get them off here. Yeah, is that fine for number 2, guys? For 3a, they asked you now to factorize. I can't remember, did they say using the factor theorem? I don't think so. I think they just said factorize fully. Okay, so then you didn't actually have to write the stuff on the left, on the right, sorry, on the right here. You could have just factorized. Okay, but I just showed that the first value that worked for me was positive 2. But guys, you only do this if the question says using the factor theorem. Okay, so maybe I'll add that there just as a note. Only add this. Only if factor theorem, if they say in the question, use the factor theorem or by factor theorem or something like that. Only if factor theorem is in the question, otherwise you can just factorize normally. No, it's just a waste of time. Yeah, so we'll just take the time for our yes. So we don't really look at that one, but when we look at what I have here, you will get minus 22 x if you multiply out. So if you do that product, that's going to give you an x squared, that's minus 20. And then if you do this product, that's minus 2. So you can look at that. Yeah, so what I would do is I look at the equation. But whatever works for that one will work for the other one. Okay, same thing for B and C. I will just show you there the factorizing there for all of them. Again, it doesn't ask you to solve for x, so please don't write x equals blah blah blah. Alright, it's just factorizing, so that's all you have to write down. Any questions on any one of these three? No? 6 and 1. So if you do 6 and 1 here, then when you add them, it's going to give you 7. Hold on, and you want negative 5. So it has to be 3 and 2. So that's not going to give you your final term because you're supposed to get positive 6 in the last term. So if you have a +1 and a -6, that's going to give you -6 when you multiply. Okay, so for this, a way to remember is if your last sign is positive, then both of the signs in the brackets are going to be the same. That's like a shortcut. So if that's a plus, then both of your signs are going to have, both of your brackets are going to have that sign. Any other questions, guys? We are going to use this factorizing thing still quite a lot when we actually draw cubic graphs. Okay, so we're going to do that in a little while, where you're going to get an equation like this, and we're going to have to do this factorizing and solving for x to get the x-intercept. Okay, so we are going to still practice it a lot later on. Number 7. Okay, they gave you this information. They said 2 minus x is a factor of this cubic function or expression. And then they ask you to solve for p. Right? Now guys, if you have a bracket 2 minus x or x minus 2, right? 2 minus x, what x value will make this bracket 0? 2, hey. So if this is a factor, then the x value that you'll get from that factor is 2. Right? It's just a bit strange because it's 2 minus x. Normally we write x minus 2. But do you agree that if x is 2 here, you're going to have 2 minus 2? Right? So x equals 2 will give you an answer of 0. So what I did was I thought, okay, I have an x value here that will make this equation true, right? That will make the remainder equal to 0. That will work. So why don't I just sub that x value in? Because if I sub in x equals 2, then I just have one variable left, which is the p. Okay, so that's what I did. So they're telling me that 2 minus x is a factor of this. And if it is a factor, remember, if it's a factor, then it means that the remainder, when x is 2, is going to be equal to 0. Right? Do you remember that from yesterday? If the remainder is 0, then something is a factor. So how do we find the remainder? By subbing in the x value into that equation. Right, that's how we find the remainder. So the remainder will be 0. So that is the remainder there, where x is 2. And then we just solve for p from there. So that was a bit of an application type question. Okay, if you're done marking, done copying that down, then I want you to please stop reading through that page that I handed out to you and just look at what they are actually asking you to do there. Now guys, that page is a bit complicated. Can you do that again? Okay. That page is a bit complicated. It's actually a proof of a formula that you're going to use. I don't really want to just say this is derivative and this is the formula and we're going to use it. Yeah, I do want you to understand what's going on. So guys, all of that stuff where you're working with the graph and you're finding a gradient and you it's all going to end up, if you look at the back of that page, right? If you look at the very last line on the back of that page that I handed out to you, it says the derivative is equal to, and then there's a formula, right? We're going to be working with that formula. So that whole page, the front and the back, is all working towards actually making you understand where that formula is coming from. Okay, so it's not a proof that you have to know. It's not a proof that you have to be able to do. We're just going to end up getting to that last. So if you're looking at the back of the page that I handed out, it says the derivative is equal to, and then there's a formula. So I'm going to explain to you now where that formula comes from. Yeah, okay. Yeah, can I get my one outside? Yeah, please. Okay, now guys, before we look through that page, I want you just to write something down. And this is going to be, it's almost going to be going back to gradients. We spoke about average gradient on Monday, right? Yeah, right. Spoke about average gradient on Monday. We just write this down. We're kind of going back to gradient now, okay? I think I told you that when we're doing calculus has to do with the study of change. And yeah, it's a bit abstract. But how does the graph change? It's the gradient of the graph. It's how it changes, right? How it slopes up or how it slopes down. All of that has to do with gradients. So we're going to be talking about gradients a lot. We're going to be talking about curves a lot. We're going to be talking about change of gradients a lot. Okay, so again, just bear with me. It's going to seem quite abstract. Hopefully, at the end of this lesson, we understand where the formula comes from. Okay, that's what our focus is today. So if you just copy this down quickly, it is kind of a bit of a repetition of what we spoke about on Monday. But on Monday, we spoke about the gradient between 2 points. When we're looking at what I've written down here, we're talking about the gradient at a specific point. So it is slightly different. Okay, once we copy this down, we are going to discuss it. And then we'll look at that page, but I'll just give you a few minutes to copy that down. And guys, this all is very theoretical at the beginning, so it's going to seem like it's going to be very complicated. But when we actually start using the formula, it's not that bad. Okay, but you unfortunately have to know like the background of the formula before we can. And the background is quite complicated, but the actual formula itself is not. What if I can get to Okay, guys, I'm just going to start talking through that. I think most people are done. So, rate of change is a term that we're going to work with also going forward, but basically, rate of change is the gradient, right? So, if you want to add that here, you can maybe just add that at the top. The rate of change of anything, actually, we're going to apply it to like real world examples as well. Okay? Thank you. Rate of change, we're going to talk later on, I think only next term, we're going to talk about rate of change in terms of like when you are accelerating the car, for example, you're changing the speed, all right? The rate of change of anything actually is always the gradient of that function. Right, most things in life actually, I don't know if you guys are aware of this, but most things in life can be expressed in terms of a function. All right, so rate of change of any of those things, for example, next term is always the gradient. So here they're saying the average gradient is equal, well, the average rate of change, sorry, it is actually there, it's equal to the average gradient of the curve at the point of interest. Now, at this point, this is different from what we did on Monday. Okay, Monday we calculated the average gradient between 2 points. Do we remember that? Right? You calculate the y values of the 2 points and you use the change in y over change in x formula. So there we have the formula for gradient. Now, guys, if they're asking you to find the gradient of the curve at a specific point. So if you only have 1 point, right? You can't use this formula if you only have 1 point. What do we need to find the change in y over change in x? We need 2 points, okay? So what we're working towards is getting a formula that will actually give us the gradient of a curve at a specific point, instead of at 2 points or between 2 points. All right, I'm just quickly going to go back to Monday's. I can't remember if I drew a diagram. On Monday we did this, right? We had this gradient of a curve. Now, guys, if you were drawing a line going through those 2 red points, for example, that line actually isn't really on the curve. I don't know if you guys can visualize that. Right, that line will kind of cut through the curve. It will be on one side of the curve here and on the other side of the curve there. So that's not really going to give us an accurate gradient, an accurate rate of change, which is why we're moving away from between 2 points to at 1 point. Okay. Sorry, you won't understand what I'm saying just yet, but we're going to get to it. Okay, so now they're going further and they're saying the gradient of a curve at a point is given by the gradient of the tangent at that point. What is a tangent again, guys? It's a line that touches a curve at only 1 point. All right. So now instead of having 2 points on the curve, we have 1 point. Okay. And what are they saying here? The gradient of a curve at a certain point or at a specific point is given by the gradient of the tangent at that point. Okay. You'll see now we're going to talk about that a lot in this handout. And then what they're also saying is that the gradient of a curve is different at each point on the curve. All right, there is actually a note on Google Classroom. I just want to show you just the picture. You don't have to copy it down. I just think it's quite a nice way of just understanding what they're saying there in terms of the tangent. So let me just bring that up quickly. I don't know if you guys have seen on the grade Google Classroom, there's like a 35-page note on calculus on there. If you ever feel like you want to do some reading. So it's this. So this is what they're talking about, guys. Let's just quickly look at this. Hello, here we go. All right, here we have a curve, right? The parabola. We're not going to draw this now, guys. Don't worry. I just want you to see something. If we're looking at point E, how many tangents do you think can exist at point E? Only one, right? So what they're saying is that if you have a tangent, and I think it's this purple, what did they do here? This purple line is between E and G, all right? But if you draw a tangent at point E, I think that is the red line there. You guys see that? It's almost like a longer dot. It's like a dot, like a line and a dot, line, dot, right? Let me zoom in a bit more. So this line here, the red one, is the tangent at point E. Do you guys see that there? Now, guys, that gradient of that tangent is different from the gradient of the purple line, right? And if we had a tangent at F, they didn't draw that one in, but that tangent will have a slightly different gradient from the tangent at E. Okay, so what I'm saying in this note here is that the gradient of a curve is different at each point on the curve. Okay, that's so at point E, the gradient will be different from at point A from at point G, because you have a different tangent at each of those points. Maybe we should add that there. So the gradient of a curve is different at each point of the curve. Maybe let's just turn that into a comma, because there is a different tangent at each point. Okay, so guys, are we understanding that the gradient of a curve at a point is the gradient of the tangent at that point? Okay, we're gonna write it actually on this page as well. So on the handout that I've given you, we're gonna start looking at that page now. In this gap here underneath the equation, I please want you to write that down, guys. Guys, can we stay focused, please? Because every time you get off topic, you're gonna forget what I said. I mean, I'm gonna have to explain the whole thing again. And I'm really not in the mood for them today. Okay, please write that down there. The gradient of the curve at a specific point is equal to the gradient of the tangent to the curve at that point. So this is now on the handout, right? On the page that I gave you, just underneath that equation. And I suppose we can call this almost like an investigation. Okay, we have a certain aim on this page. The aim is to find the gradient of f, which they have drawn for you on the side here, at the point 1, -6. So now we're going to try and find the gradient of this curve at a specific point. All right, if you want to, you can actually highlight that at the point 1, -6. That is the whole purpose of this investigation thing that we're doing. We know how to find the gradient between 2 points. We want to come up with a formula that will allow us to get the gradient at the point. Because like I said, we can't use our change in y over change in x formula if we only have 1 point. All right, so we need to come up with a new formula. So guys, what they have here is they've given you the picture, right? We will look at it just now, but what I want you to do quickly on your own now, they are giving you different points on this graph, all right? So they're giving you 1, -6 each time. We're going to keep working with 1, -6, all right, in each of these calculations, but they are wanting us to calculate the gradient between these 2 points. These are always 2 points that lie on this graph. Okay, so they're saying find the gradient between 1, -6 and another point on the curve. That's the first thing that we're doing. So they're saying when x is 2, y is -3. Let's look at the graph. Can we identify that point? Do we have the point 2, -3? 2, oh, it's over there, and then -3. So that is the first point that they're giving us to work with. Yes? No, so we're never actually going to do this in a test or exam. This is just coming up with the so this is almost like the proof that we do. Okay. So we're starting with what we know. We know how to find the gradient between 2 points. So we're choosing 1 point, 1, -6. Maybe circle that one, guys, because that is the one that we're working with every single time. That is the point that we want to find the gradient at. All right, at the specific point. If you want to, you can maybe take a ruler and try and draw in a tangent there at that point. You can just kind of guess what it would look like, all right? Oh, that didn't work. Kind of, all right, so it's supposed to touch the graph just at that point. Okay, I'm going to fix it now. Mine is a little bit off, but just draw in. So this is what we're actually trying to find, guys, the gradient of this tangent. Okay, but what we're doing first, and you're going to do it now on your own, is you're finding the gradient of the line between these 2 points. Okay, those are the 2 points that they're asking us to work with for the first calculation. How do you find the gradient between 2 points? Change in y over change in x. Okay, so I'll do the first one with you, then you're going to do the rest on your own. So change in y, we're going to take this y value, -6, minus the y value of the other point. I'm just using that line there as my fraction line. Over change in x, 1 minus 2. Okay, are we getting an answer of 3, I think? What I have here. Okay, now for the second calculation, guys. Now they're saying, now move that second point closer to the first one. So instead of choosing a point 2, 3, which is quite far from this point, right? We want this gradient. Now, guys, if I'm calculating the gradient between these 2 points, that is what I'm finding. That's obviously very far off of this gradient. Okay, so let's choose another point that's actually closer to this one, because then we'll get a gradient that is closer to the one that we're looking for. So they are now choosing the point 1, 5, -5. Okay, so on the picture, I'm just going to show you where that is. 1, 5, and -5. It's now that point. That's the second point that they're asking us to work with. So in the second calculation, you're finding this gradient. Okay, by doing change in y over change in x. Do that quickly on your own. It's in the second line. I wrote it down already while I was talking. Okay, for the second one, guys, I'm getting an answer of 2. Right, you as well. Okay, so we're again doing change in y over change in x, and we're getting a value of 2. Now, guys, the gradient of 2, right, this gradient is closer to the one that we're looking for than the first one. Okay, but it's still quite far off. Can we see that? These 2 gradients are obviously very different. Okay, so next up, you're now going to take another point that's again closer. So 1, 2, hey? So 1, 2, and this one, please work out what this gradient is, and you're going to keep going down, right? Please calculate the gradients of the next 3 parts there, points that they've given you, and we'll see what happens to the gradient. Okay, we calculated them, so this okay. Okay, guys, I'm just going to show you my three answers. Sorry if you are so busy. And then we'll look at the graph again. Okay, so for when we're working with 1, 2 and negative 5, 7, 2, I'm getting an answer of 1, 4 for the gradient. Then when I'm going even closer, right, remember the point that we're trying to find the gradient at, point that the tangent is at is 1, negative 6. So guys, what I want you to notice is that each point that I'm choosing is closer to that point, closer to 1, negative 6. We started with a point 2, negative 3, 2, negative 3, right? Then we went back from 2. Remember, we're wanting that tangent at 1. All right, so now instead of 2, then we did 1.5. Now we're going even closer. Now we're doing 1, 2. Then we're doing 1, 0, 5. The gradient there is 1, 1. Then we're so close to this point, guys. You see that 1, 0, 0, 1. That's almost on that point. Then we're getting a gradient of 1, 0, 0, 2. So what is happening now here, guys? Do you see that the gradient, the closer we get to that point, the gradient is getting closer and closer to 1. Right? Do you see that? If we chose a point that was even closer, so say we did 1, 0, 0, 0, 0, 0, 1, and whatever that y value was, it would be even closer to 1. It would maybe be 1, with more zeros. All right? Yes. Almost, not exactly, but we are going to an infinity kind of thing. Yes. Okay, so you're almost on the right track. Yes. So let's analyze what we have discovered, guys. As the second point got closer and closer to the first point, that's what we did every time, the difference between the x values got very close to 0. Okay, let's highlight that. That is important. The difference between the x values got very close to 0. Right? First, the difference between the x values was 1 unit. It was from 1 to 2. Then it was half a unit. It was from 1 to 1,5. Then it was 0, 2. Then it was 0, 0, 5. Then it was 0, 0, 0, 1. All right, so the distance between the 2 points, the distance between the x values, got very close to 0. And then the gradient went from 3 to 2 to 1.4 to, okay, so they just actually listed everything that we just calculated. But what that actually means, guys, they're saying here, so it seems that as the distance between the points tended to got closer to 0, the gradient tended to or got very close to the actual gradient of the curve at that point. Actual gradient of that tangent, guys, was 1. Okay, if we went closer and closer, we would have seen that. All right, which was actually a gradient of 1. So let's highlight that as well. The important thing here is the distance between the points tended to 0 and the gradient tended to 1. That tending to is a new concept. We haven't really worked with that before, except for sum to infinity, where we had some concept of a value is getting closer and closer to a number. Okay, it's a similar kind of concept. So now, in the very last sentence on that page, they are saying, so we would say that the gradient of the curve or its tangent at the point 1, negative 6 is equal to 1. Okay, but it took us a very long time to work that out. So we want to come up with a general formula so that we can get the answer by just subbing it in. Okay, instead of calculating 5 different gradients and then making a conclusion. All right, next page. Now this is interesting, guys. I really need you to try and focus on this picture now, because now we're going to do what we did in terms of numbers on the first page. We're now going to do in terms of variables on this page. Investigation. What is that investigation? Oh, that's that circle thing. Yeah, well, they kept forever. Yeah, you did. Yeah, that's true. Okay, guys. All right, let's look at a more generalized version. So we've looked at an actual version, a numerical example, and we got that the gradient was 1. How did we get that the gradient was 1, guys? By calculating the gradient between 2 points and getting closer and closer to the actual point. So what did we do with the distance between the 2 points? The distance became closer and closer to 0. Okay, do you remember that? We highlighted it on the previous page. So that is important. So if you're looking at the picture, guys, they are explaining exactly what all of the variables represent. So f of x is a function of x. We know that, right? F of x is the name of the graph. Okay. If we look at this, we can see that this function looks like a parabola. It can be any curve. Okay, but we are familiar with a parabola. The previous example was parabola, so we're working with a parabola here, but it can actually be any curve. All right, let the point that we want to find the gradient at be xy. So now instead of y negative 6, we're working with xy. So guys, look at what they're doing then. Now they are replacing the y with f of x. We know that f of x is the same as y, right? If you have your x value of a point, how do you find the y value of that point? By subbing it into the function. Okay, so they're saying that y is now just represented by f of x. So guys, whenever you see f of x, they're talking about y. Okay, but we did kind of know that already. All right. I'm sorry, let me just go to this page here. Okay. Let the distance along the x-axis from this point to the second point be h. All right, so if we're looking at the picture, what do we have here? They've given us a point, right? This point P, this is the point x, f of x. That is point P, all right? That's point P. Maybe you want to just label that point. Let's add the P there in front as well. They didn't actually label it on the picture, all right? But that is the point that we're looking at. We are trying to find the gradient now at this point. X and f of x. Now they say we're choosing a second point. All right, the second point is Q. The distance between the first point and the second point is h. You see where they've indicated that there. From this value to that value, that is the distance. So guys, if P is the point x, f of x, what is Q going to be? Let's think about that quickly. If P has an x value of x, now I'm adding h units to it. What is the x value of Q going to be? X plus h. Right, so that is the original x value, the value of P, but I'm now adding a distance to it. Okay, whatever that distance is. That distance is represented by h. How would I then find the y value of that function? If the x value is x plus h, the y value is going to be f of x plus h. Okay. Have I lost anyone? All right, so we have the original point, point P. I'm now adding a distance of h to that point to get the second point. So the second x value is x plus h, and the second y value is going to be f of x plus h. All right, these 2 points both lie on the same graph, right? They both lie on x. Are we okay with that? So guys, how did we find the gradient at point P? We continuously calculated the gradient between these 2 points, right? Any 2 points on the graph. But what happened to the distance between them? What happened to the h value? The h value got closer and closer to being 0, right? I moved that second point closer and closer to the first one. So by moving it closer, I'm decreasing the h value. I'm making the h value get as close as possible. There's this x value. I want to get as close as possible to the original x value. So what we're doing is we are making h get closer and closer to 0. Okay, so let's just quickly read what they're saying here. Let's also highlight this. The distance along the x-axis from this point to the second point is h. That's important. Okay, that is indicated there. There we have h. And now I think they are also giving the coordinates of the second point, but we already wrote that down. Okay, so the second point will be x plus h, and then the y value at x plus h, which we get by subbing it in like that. Okay, so we did already indicate that on our diagram. We've done that already. Okay, so that is q. Now the formula, they're saying point 1 is that. That's P, right? We're almost there, guys. This is point P. This is point Q. All right, those are the coordinates. How do you find the gradient between 2 points? Change in y over change in x. Okay, so they are taking this y value minus that y value. Do you see that that's what's happening at the top there? Change in y. Right, change in y over change in x. So they're taking the y value of q, if you want to add that in there, minus the y value of p. That's what they're doing for their change in y. They're taking that y value minus that y value. Right? Then they're taking the same x value minus the same x value there. All right, the x value of q minus the x value of p. And then they simplify it. Okay, we can't actually simplify that. Those will be two different y values. We don't know what that is. But if we have x plus h minus x minus x is 0, right? So when we actually simplify that, we're left with just an h at the bottom. Guys, do you have your formula sheets with you? Maybe in paper 2 book. Can you just look at those formula sheets quickly? I wonder if I have mine here. Yeah. We notice that, guys, that looks very close to what we have at the moment. Sorry, it's quite gray, all right, but there it says derivative by first principles. Now, I don't know what that means yet, but do you see that we have that part of the formula already? Now, what's this limit as h tends to 0 thing? Limit, you've heard of limits, hey? Have you watched Mean? You've never heard of it, please. The limit does not exist. Yes, we are going to do that as well. All right, so limit h tends to 0. But what is h again? The distance between the points. So how do we find the actual gradient? By making h tend to 0. Okay, so let's see where does that. There we go. And as h tends to 0, the gradient will approach a limit. We are going to discuss that still, guys. Don't be put off by that. But this is important. H tends to 0. All right, and they show that in the equation by saying limit. I normally just do a cursive L. I'm not sure why. Actually, you don't have to. It's just a habit. As h tends to 0, that's what you do. That's how you're going to show that the distance between the 2 points that you're choosing is getting closer and closer to 0. It tends to 0. Okay, that's the like mathematical terminology. This formula. All right. So you're going to write that after your limit h tends to 0 thing of f of x plus h minus f of x. And that is all over h. Remember, change in y over change in x. That's where we got that from. And guys, this is basically the gradient of the tangent at that point. Yes. Yeah, there shouldn't actually be a line. I'm not sure. Yeah, I'm not sure why. I think they entered it as a fraction, but there shouldn't actually be a line there. Yes. Yes. Yeah, you can see that on the formula sheet. They also wrote it like that. Yeah. Okay. I think it's just like a shortened way of writing. Okay, so guys, now we're getting to the summary. Okay, finally. This is basically the formula that we were trying to prove. Like I said, you're not going to have to do this proof. So if you're feeling absolutely lost, don't worry. I'm going to show you how we apply this formula. It's different from the proof that we've just done. Okay, I hope obviously that you understood what I did this now, but if you don't, it's not the end of the world. This is important. Please highlight this. The gradient of the curve at a point is equal to the limit that is approached as h tends towards 0. Okay, that is quite long. So the gradient of the curve at a point is equal to the limit. You can actually just say limit as h tends towards 0. And we get that by using this formula, guys. So I'm going to show you. So let me actually see if I can just do this. Sorry. Let's do that. Okay, so that's the formula that we're going to work with, guys. Now, another thing that you don't know yet, you have seen the word derivative, right? You've seen it maybe if you work through past papers or something, or maybe just in general, you've seen the word derivative. Right, the derivative is basically just the gradient. Okay, but we're going to apply it in different, so what I'm looking for, different contexts as well. So it's not always called the gradient, but it is essentially the gradient. So that is something that's also important. The gradient of the curve at a point is also called the derivative. And we are going to have different ways of calculating it, but whenever you see the word derivative, they're actually talking about gradient. Okay, whenever you see the word gradient, you can actually also just find the derivative. Okay, derivative and gradient, those are always the same. Gradient, derivative, derivative, gradient. So therefore, when we're saying that the gradient is equal to this, we can also say that the derivative is equal to this. Okay, so this is not only a formula for gradient, it's also a formula for derivative. Now, I just very quickly want to show you how we're actually going to apply it so that you don't feel completely lost. Like I said, this was the proof. This was just me showing you where this formula is actually coming from, but we're not going to use it in the way that we prove it, right? We know that, hey, when we've proved geometry theorems, we don't use it in the same way. Okay. Let's do an example. You can actually make a new heading if you want. We have 10 minutes. We're going to finish it in these 10 minutes, guys, and then you're not going to have homework for the long weekend. No. Finding the derivative / gradient by first principles. That is the heading, please.
Well, let's put them the same here.
No, I don't think so. First principles is basically going from like the definition of what is the derivative, what is the gradient. So guys, whenever you see the words first principles, you need to use the formula that we just proved. Okay, there is another way of finding the derivative, which is much quicker, which I'll show you next week. But whenever you see the words first principles, you're going to have to use the formula that we just proved. Yes. I really don't know. I think it comes from an understanding. I mean, it's in the curriculum, so there's nothing I can do about that. Yeah, there's always a question like this in the final exam, 5, 6 marks. Always the same issue. All right, are we ready? Huh? Find the derivative of f of x equals x squared minus 2 at the point, I'm going to still say that, yes, by first principle, that's what it says at the end. Sorry, I was just quickly find a point that actually lies on this graph. Yeah, okay, that was easy. At the point 1, negative 1. By first principles. Quickly, guys, I want to finish this. So when you see the words first principles, we are going to have to use this formula. Now, guys, for derivative, you can say m equals, but the actual the notation for derivative also is f dash x. Okay, so it's f with a little, like an apostrophe, basically. They call it dash, but it is essentially an apostrophe. Okay, you mustn't be confused with inverse, right? What was the notation for inverse? It was a minus 1. Okay, f to the negative 1. This is now f to the apostrophe x. Yeah. In the context of probability x, but not in. Okay, so guys, f dash x, that's derivative. So that is why on your formula sheets, that's what it says. Hey, it says f dash x is equal to this formula. Okay, so it says f dash x is equal to the limit as h tends to 0. So guys, that h tends to 0 is almost like a subscript in a sense. And then you have your fraction f of x plus h minus f of x over h, and this is on the formula sheet. Okay, you don't have to memorize this formula. It is on the formula sheet. Now guys, on the side, I would suggest that you calculate your f of x plus h. All right? If we're looking at this formula, I need to sub into the formula f of x, which is x squared minus 2, but also f of x plus h. All right, so I'm going to write that on the side. F of x is x squared minus 2. And f of x plus h, this is what you have to calculate in order to sub it into the formula. Now guys, if the function is x squared minus 2, now I'm saying instead of x, I need to use x plus h. So instead of x, I'm going to put x plus h. All right, so where I have x squared, I'm going to say x plus h squared minus 2. All right, we've done function notation before. Whatever is in the brackets, you replace the x with. Right? So if it was f of 3, you would make your x equal to 3. Now it's f of x plus h. So you have to replace your x with x plus h. Okay, that's what you're always going to do. So see, completely different from what we just did. Completely different from the proof. Now we're going to multiply this out. Guys, remember that this is the same as x plus h times x plus h. All right, I'm going to rush through this, guys, because I don't want us to leave an example for 4 days and then try and come back to it on Tuesday. It's going to be, it's not a good idea. All right, I'm going to multiply that out, we get that. Now we're going to sub that into the equation, into the formula. So we're going to do this minus in brackets x squared minus 2. Okay, I'm just going to do that quickly. Guys,